As Sergio has told, I'm Jordi Mompart, Associate Professor at the Autonomous University of Barcelona, and I'm in duty of, let's say, or in charge of, responsible of the quantum optics and quantum technology subject. That more or less they form a speciality, although you know that the students, they don't take a speciality, they choose subjects, okay? And this quantum optics and technology is formed by 6 subjects. The first one is called quantum optics. And this one pretends to provide the student with the basics of quantum optics. So this means that, for instance, those students that they have done quantum optics in the bachelor, in the physics bachelor, for instance, they shouldn't take this subject, quantum optics, because it's going to be more or less the same. It pretends that those students, for instance, engineers or physicists that they have not done quantum optics, then they will do it in the master. Then this subject has to do with the so-called red atom, Rabi oscillations, dipole force, quantum Rabi oscillations, James Cumming model, etc. This means basically it has to do with light-matter interaction in the so-called semi-classical approximation and the quantum approximation. Okay, it's the first approach to let's say quantum optics and light-matter interaction. And then there is a second subject called from cooling and trapping of neutral atoms to Bose-Einstein condensation. In this case, we teach, for instance, all these techniques, all the techniques used for cooling of neutral atoms, for instance, laser cooling. We also teach how to reach Bose-Einstein condensation. Also, we derive the famous equation called Gross-Pythagorean equation that gives the dynamics of Bose-Einstein condensates. We talk about atom lasers, matter wave solitons, and in general about atom optics with, let's say, with matter waves, with matter. Then there is a next subject that is called quantum simulators with ultra-cold atoms. In this subject, what we do is the following. We teach how to trap atoms in, let's say, optical lattices. Optical lattices are like crystals created by laser light. If you send counter-propagating lasers, you can create trapping positions and reproduce or mimic like crystals with electrons, but in this case with neutral atoms, and the traps are optical traps. Okay. In this case, we have some very famous model that is called the Bose-Hubbard model. We investigate this model in the so-called Fourier space, the band structure, etc. And this is very interesting because it allows us to simulate the physics of condensed matter systems. For instance, we can simulate superconductivity with ultra-cold atoms in optical lattices. We can investigate topological insulators or 2D topological insulators, artificial gauge fields, artificial magnetic fields, etc., using these quantum simulators. Then we have a quantum information subject. This quantum information subject is an introductory subject in quantum information. Probably also some of you have done also this subject in the bachelor. In this case, if you have done the subject in the bachelor, what is going to happen is that the tutor of when you try to register in the master will tell you not to choose the subject, quantum information. Okay, and it has to do with quantum communication, quantum cryptography, quantum computation. You will see the definition of quantum bits, quantum gates, and quantum algorithms. It's a very mathematical subject. Okay, and next we go again to a physical subject that is called advanced quantum optics applications. In this case, it's like the continuation of quantum optics but with photons, single photon sources and detectors. So we talk about coherent states, vacuum, squeezing, quantum coherent correlation functions, photon bunching, anti-bunching, and all these experiments that we have to do, for instance, with single photons, like in quantum cryptography. And finally, there is a last subject in this collection of subjects that is called machine learning on classical and quantum data. And it has to do with artificial intelligence, but based on machine learning, and particularly based on neural networks. And we provide theory, and we give examples, you do some simulations, and finally you reach also to a very hot topic presently, that is quantum machine learning. And you will see that quantum optics and quantum technology in principle, they are two different things, but at the end, 99% of the implementation of quantum technology, they have to do with quantum optics, because either photons or lasers play an important role in these implementations. For this reason, all those that are interested in, let's say, in the implementation of quantum technologies, it's good to take this quantum optics subject. But look, you have 6 subjects, so this means 18 ECTS credits, okay? And you can choose up to 24 credits for subjects, for elective subjects. So this means that you have also 2 more subjects to choose among with for your curriculum. And then once you have finished with let's say with the mandatory subjects of the master and the elective subjects of the master, you will have to choose also the master thesis. It's important to note, Krina also said that every year we have proposals, okay, from professors and researchers, and not only from, let's say, from the institutions that participate in the master, but also from, let's say, foreign institutions even. And we have like 50 proposals, and we have 35 students. So this means that we have more proposals than students. And a lot of them, they have to do with quantum, because quantum is something that is being done in the Autonomous University, also in UTC, also in UAB, but also in ICFO. In ICFO, there are a lot of groups that they work in quantum optics related subjects, okay, and they offer a lot of proposals. So don't worry, because if you want to do a master thesis related to quantum optics, for sure you will have a proposal on quantum technologies. Also, there is the possibility that you contact with someone, let's say, outside of the master, working in quantum optics, and then with a tutor from the master, a professor of the master, then you can do this master thesis, let's say, with a professor outside, let's say, of the main institutions of the master. This happens quite often every year with, let's say, with a couple of students. Okay. Another thing that I wanted to tell you is what happens when you finish with the master in photonics. Most of the students they go to and they do a PhD. Okay? But think that that's not the only possibility. You can go to as a consultant or engineer to a photonics company. You could go to you could work like a technical in a technical position in a laboratory working with, let's say, for instance, with lasers. You could even create your spin-off with a revolutionary idea or something like this. Okay. In this sense, it's good to know that 1 year ago we did a survey among our students, the ones that finished in the promotions of 2015 to 2018. Okay, and 43 students they answer the surveys, and you can see here that more or less they answer more or less the same in the different promotions. Okay, and what did they say? The first thing, and which is very important, is that we did the following question: how long did it take you to find a position after graduation? And the very, let's say, nice result is that more than 75% of the students they need less than 3 months to find a position, which is really good. Okay, almost instantaneously after finishing the master, they got a position. Okay, if you go to 1 year, 95%. Okay, so it's quite easy to find a position after graduation. Okay. The second thing, which was your first position after graduation, and you can see that 64% they did a PhD, and this matches with the initial interest. Most of the students that they do this master in photonics, but not all of them, they want to do a PhD. And it's also important to say that a significant portion of the students, let's say 20%, okay, they went to a photonics company after finishing the master, which is quite a good result. And some of them they also went to other companies. So 30% more or less they went to companies. Okay. Another question which is important is to which country? Okay. And again, 64%, let's say in Spain, and the rest in different countries. And the one with, let's say, with a second most highest percentage was Germany. And this has to do also with the fact that we have always German, French, let's say Italian students, okay, also from Iran or from Iraq, okay, and some of them they come back to their countries to work for a company, but it's not always this the case. Even Spanish students they go to Germany to work, or to France to work, etc., and they find a work there. Then the next question we did the students was, if you started a PhD, which was your main research field? And again, an end result, you can see that the colors are more or less the same. And so some of them they did quantum optics, or others optical engineering, others biophotonics, etc. So this means that the fact that in the Master of Photonics we teach all possible subjects, let's say in photonics, is a good thing, because the demand for PhD students and in companies is also very spread in the different subjects. So this reproduces very well the demand and the offers that the students they will offer later. And also we asked those students that they went to a photonics company, which was her photonics sector. Okay, and you can see that most of them, green, they went to work with companies related to optical sensors, optical tests, etc., and measurements. And finally, is your current professional career related to photonics? And more than 90% said yes. Okay, so this means that our Master of Photonics has really a good reason to stay here. Okay, because almost all the students at the end they work in photonics. So with this, I finish. And if you have questions, please.